Okay, gang, we're going to come back to tank problems again. We did them back in the first chapter, I think it was, or second chapter, when we had one tank and we wanted to know how much solution or how much salt was left in it at a certain time. And that required first order linear differential equations. Now that we have systems of differential equations, we can deal with two tanks, and we can look at these two tanks interchanging solution between them. So this is just a nice example to show how systems of DEs can be used and might be practical in some actual real life situations if you're dealing with this sort of thing, and it makes it nice for making interesting problems as well, because you can change the problem to allow you to practice different kinds of solutions. So let's get going. So this is the one from the book. You've got 5 more to do on your own, I think it is. But this is the one that's in the book, and let's go through it carefully. So you have, you start off, and this is what you always need to do, is to draw a picture of it and get all the information on there. It makes it much easier to look at a picture than it is to keep going back to a paragraph and trying to glean the material out of a paragraph. So in this case, you have 2 tanks that are each 100-gallon tanks, and they're each filled with solution. Okay, so you need to indicate that on there. I'm calling them X and Y, capital X and capital Y. Tank Y has 150 pounds of salt dissolved in it, so that's got salty solution. This is just pure water over here. And at time equal to 0, you start the switch, which starts sending water going in this direction from X to Y at 2 gallons per minute, and also water going from Y to X at 2 gallons per minute. And you need to, one of the assumptions you make when you do these is that all this solution is being constantly stirred in these tanks, right? If it weren't being constantly stirred, depending on where the salt was coming out and where it was going in and so on, it might be more salty in one spot than the other, and that sort of thing. So that's an assumption that we have to make. So as with any applied differential equation problem, story problem, you need to start with the word let. So let x of t, small x of t now, be the amount in pounds of the salt in tank X at time t, and similarly let y of t be the amount of salt in tank Y at time t. The only reason I don't write that down is just because this is all the amount of space I have, but on your own paper you should write that down as well, obviously. Okay, so here's the key thing we need to do, is we need to come up with a way of describing what's going on in those tanks, describing that mathematically, and that's what mathematical modeling is all about. That's what we need to do here. So very similar to what we did in the earlier problems. What do? We say, okay, let's look at how the amount of salt in tank X is changing. So salt is coming in and salt is leaving. Here's the rate at which salt is coming in. First of all, the salt is coming in at a rate of 2 gallons per minute. So there you have it right there. And each of those gallons has how much salt in it? Well, at any time t, the amount of salt per gallon is just the concentration of this tank. So in this tank, at any time t, you have, that's why you need to have that written right here. Y of t is the amount of salt, and you've always got 100 gallons of solution. So the amount of salt divided by the amount of solution, there's your concentration of salt. So this is, if you had units here, this would be pounds of salt per gallon, and then this would be gallons per minute. So if you have pounds per gallon and gallons per minute, the gallons leave, and you end up with just number of pounds of salt per minute, which is what you want. This is the rate at which the salt is entering this tank in pounds per minute. Okay? What's the rate at which the salt is leaving this tank? We're going to subtract that. Well, in this case, it's leaving at a rate of 2 gallons per minute, same as before. And in this tank, of course, you have at any time t, you have x pounds of salt in it divided by 100 gallons. So x divided by 100 is the concentration of salt in this tank. So again, pounds per gallon, gallons per minute. The gallons cancel and you end up with pounds per minute. So this is a pretty basic problem. The ones that you're going to be doing are a little more interesting than this, but this one is nice for teaching the basics. So then I'm going to write it as I always do. I'm going to write it as the x first. So it's going to be negative x over 50 plus y over 50. So that's that one. So tank y, mutandis mutatis. That is, you make necessary changes. It's going to be the same sort of thing. And so it's the rate at which the salt is coming in to tank Y. There's the rate at which it's coming in. Here's the rate at which it's leaving. And so you get the same sort of thing. Notice that these are just the opposites of those, because it's exiting this one and it's entering this one. It's exiting this one and it's entering that one. The amount of salt is always going to stay at 150 pounds. In fact, if you wanted to, you could actually write here. This is going to be important in one of the other exercises. You don't need it here, but x plus y is equal to 150. Agreed? X plus y is always going to be 150 in this particular case. No new salt is being added. No salt is leaving the system. So if you needed to, you could actually replace one of these. You could replace this y, or you could replace this y with x, and you could get a differential equation of just one variable, and you could actually do it the way we did it back in earlier chapter. Okay, but anyway, we'll do it this way because it shows what we can do in the next problems. So here it is. Now we want to write this in matrix form. So negative 150, 150, 50, negative 150. And this, of course, is the vector x vector, which, of course, you can just write as xy if you prefer. And you can either write this like this, or you can write it as x prime on top and y prime on the bottom. Okay, either way. So now we need to find the eigenvalues. And the way you find the eigenvalues is you take the determinant of this matrix with lambdas subtracted down the diagonal. And so when you do that, then you take the determinant, and that's going to be, look at all these negative signs. I have this whole thing with negatives and this whole negatives. I might as well turn them into all positives, because negative times negative gives you a positive. So I'll just write it as lambda plus 1/50th there. And then if you multiply that out, you're going to get lambda squared. This plus this is going to be 1/25th lambda, because that's double the 1/50th. And then this times this is going to be a positive 1 over 2500, but there you subtract 1 over 2500. So when you add and subtract that, you're just going to end up with this. You can factor out the lambda, and you get lambda times lambda plus 1 over 25. And so your two eigenvalues then are going to be 0 and negative 1 over 25. So those are your two eigenvalues. So then you need to find the eigenvectors for each one. So when lambda is equal to 0, you just end up with this matrix again. And notice, as needs to be the case, one of these is just the opposite of the other. So you get the same information in one as you do the other. So I left off one small little step here. So this you could write as negative 1/50th x plus 1/50th y is equal to 0. And then I just multiplied the whole equation by 50, and I got negative x plus y is equal to 0. Okay, you can multiply by any constant you want there, and then it makes it easy for the vector, for the eigenvalue 0. The eigenvector, if you let x be equal to t, then y is also going to be equal to t, so it's just the vector 1, 1. When lambda is negative 1 over 25, then you subtract those down the diagonal, and you get this. which again you can get rid of, in this case, the bottom row. They're identical. And you can multiply the top one by 50 again and just get x plus y is equal to 0. So for this eigenvalue, the eigenvector, if x is equal to t, then y is going to be negative t. So it's going to be this right there. So now we have the overall solution. You have your two arbitrary constants, alpha times this eigenvector times e to the 0. Of course, e to the 0 is just 1. And then plus beta times this eigenvector times e to the negative 1/25th t. And recall that our initial conditions are that x of 0 is equal to 0, y of 0 is equal to 150. So you have that. So so when you stick those in, you're going to get, of course, this top portion here is your x of t, and the bottom portion is y of t. So alpha plus beta, when t is equal to 0, you're going to get alpha plus beta is equal to 0. And the bottom is y of t, alpha minus beta is equal to 150. And so you can add those together, get 2 alphas 150, alpha 75, and beta is going to be negative 75. So where do we go from there? First of all, notice that the trace value of tau is going to be negative 1/25th, and the value of delta, your determinant, is 0. See that? This is negative 1/25th, and the determinant is 0. And if you look back on the diagram in section 8.6, I guess it is, then you realize that we have a whole line of fixed points. So you know right away that it's going to be, if you were to graph it, it's going to look something like this. Let's go ahead and do it totally. First of all, for the eigenvalue for the eigenvector 1, 1, here's the eigenspace for associated with that eigenvector. If you just multiply that eigenvector times all possible scalars, you're going to get the eigenspace. There's the eigenspace right there, and then here's the eigenspace for 1, negative 1. 1, negative 1 is going to be a line that goes in the in this direction, perpendicular to this one. Basically, the line y equals negative x, and that has associated with it the eigenvalue of negative 1/25. So what's your phase space look like? It's going to be, these are all your fixed points right here, and any starting point that you are at is going to be some point like that. And what happens over time? It just heads straight towards this fixed point. So the fixed point of where you start, I should say the point where you start, that depends on what your initial conditions are. Okay? We started at what? We started at 0, 150, so we were way up here, say. Let's just say that this is it right there. And then we came in like that. Okay? So notice what's happening. One of them is increasing at the same rate at which the other one's decreasing. See that? You're coming along this line. So the x value is increasing and the y value is decreasing at the same rate. Why is that? Because the salt is going from this tank into this tank. And as you'd expect, these two tanks have the same capacity to them, and the solution is all getting spread out evenly, so you'd expect over time that this 150 pounds is going to get evenly distributed between these two tanks, and that's exactly what happens. They're both going to end up at if you start here at 0, 150, there you are at the point 0, 150, you end up here at the point 75, 75. See that? If you started with what? If you started with 100 in x and 200 in y, then you're going to be there, and then you're going to come in, and everything is going to again head towards that equilibrium where they both have the same amount. Okay, so you can learn a lot from this xy plane, the phase plane that has all this information on it, all these trajectories. Each one of these things is a different trajectory depending on your starting point. So then finally, if you take these things and say, okay, what's the graph of each one of these things with respect to time? So here your horizontal axis now is t, it's time. Now you're graphing both of these things as functions of time. And what happens? Well, if you graph these, you end up with y of t starts at 150. 75 plus 75 is 150. And then as time goes on, that's going to go to 0, and you're going to end up just having an asymptote of 75. And the opposite for x starts at 75 minus 75, which is 0. But as time goes on, again, this portion goes to 0, and you're going to build up to 75. So the sum of these two is always going to be 150. Agreed? So this value plus this value will always be 150. By, here they're very, very close to 75. Here it's 0 and 150. So there you go. And that's the kind of thing I want you to do on all these problems. Do a nice full explanation. Look at your start with making a diagram, then write the differential equations, then go through the solution, solve it, put in your initial conditions, draw your XY phase plane, okay, that has all the trajectories on it, and then also graph, when I ask you to anyway, graph both functions x of t and y of t. Okay, so there you go. So a lot of fun there. The other ones are a little more interesting, and you're going to be handing in 8.8.3, point 3 I believe it is. So let me just make sure. Yeah, right. 883 is the one you hand in. Okay, very good. So enjoy.